All right, we will go ahead and get started. So again, welcome everyone to the Fueling Collaboration Panel Discussion Series, Season 5. Thanks for joining us today. A quick introduction, my name is Lindsay Hosier, and I'm the Public Information Coordinator for the Consortium of Appalachian Fire Managers and Scientists, and it is my pleasure to be opening and closing today's discussion. Before we do get started, we do have a quick poll to get a sense of who all is joining us today. So Eric, will you please launch our poll? Thank you, Eric. So we have 3 questions that we hope everyone will answer as we really do look at the results. Question 1 is what best describes your work? Question 2, where are you physically located? And question 3, how did you hear about today's webinar? And we'll give everyone just a few moments to answer that poll. Thank you, everyone. All right, Eric, we can go ahead and close out that poll. All right, and looking at the results, we have a good mix of people with us today. We've got 40% land natural resource managers, 21% fire practitioners, 18% researchers. So that's really great. Thank you all for responding, and thanks for showing up today to this webinar. The Fueling Collaboration Panel Discussion Series is presented by the Joint Fire Science Program Fire Science Exchange Networks in the Eastern United States, as well as the Forest Service Northern Research Station and the Forest Service Southern Research Station. The goals of Fueling Collaboration are to bring together researchers and managers to learn about and discuss the latest in fire science and to build collective learning and collaborative opportunities across the region. This is our second panel discussion in Season 5. If you do like today's discussion, I welcome you to view the recordings of our past discussions. Our third panel discussion will be held on February 20th, and that is Social Acceptance and Communication Strategies for Wildland Fire Management. We did need to reschedule discussion 5.1, and it is being rescheduled for a later date to be determined. And that one is Flashy Fuels and Resilient Lands, Fueling Distinct Prescriptions for Eastern Grasslands. And if you have joined us in previous years, we are thrilled to have you join us again. If this is your first time participating, all of our discussions follow a similar format as what you are going to be a part of today. And that is a group discussion with minimal PowerPoint presentation slides. However, today we do have a PowerPoint presentation at the beginning to lay the foundation for TLS. And the discussion is built upon questions that you have submitted in advance. So thank you to everyone who did submit questions. And there are a few logistical points to cover before we do get started today. Participants will be muted and video will be turned off during the discussion. However, the chat box is open. We do encourage active participation in the chat box, and we ask that chat messages do stay on point with the discussion, and please be respectful and inclusive of differing opinions. Today's webinar is being recorded, and we will be posting the recording on the Northern Research Station website, the Fueling Collaboration website, as well as the Fueling Collaboration YouTube channel. And closed captioning is available. You can access this at the bottom of your screen where it says CC. If you just click on that, that'll engage the live captioning, and we'll also post these instructions in the chat as well. And lastly, this discussion is approved for 1.5 Category 1 CFEs by the Society of American Foresters, which we will be using the participant list provided through Zoom to submit to SAF. So please check that your name is spelled correctly on your screen. And if it is not spelled correctly, just click the 3 dots next to your name and then select Rename. Today's discussion is focused on TLS as an efficient and cost-effective and powerful tool for characterizing high-resolution sub-canopy forest and fuel structural conditions. We will hear from experts from both research and operations sharing their efforts and practical applications of TLS and other 3D wildland fuels characterization tools for improved wildland fire planning, fire effects, monitoring, and decision support. Our panelists include Dr. Michael Gallagher, who is a research ecologist and a team leader in the U.S. Forest Service Northern Research Station's Climate, Fire, and Carbon Cycle Science Research Work Unit and is located in the New Jersey Pine Barrens at the Silas Little Experimental Forest, where he is also scientist in charge. Emily Link is the regional fire ecologist for the U.S. Fish and Wildlife Service Southeast region. She has worked coordinating the terrestrial laser scanning program within the U.S. Fish and Wildlife Service in the Southeast since 2021. Dr. Louise Loudermilk is a research ecologist with the U.S. Forest Service Southern Research Station and currently serves as the fire team leader of the Athens Prescribed Fire Science Laboratory. Dr. Russ Parsons is a research ecologist with the U.S. Forest Service Rocky Mountain Research Station Fire Sciences Laboratory in Missoula, Montana. And Dr. Susan Pritchard is a fire ecologist and has worked as a research scientist for over 20 years at the University of Washington School of Environmental and Forest Sciences. And our moderator today is Brett Williams, who is a technology transfer specialist and research liaison for the U.S. Forest Service Southern Region Fire and Aviation Management. He also serves as the working group lead for the Eastern Innovation Landscape Network. And before I pass it over to Brett, I would like to first acknowledge all of our organizers and planning team. They're an incredible team, and it's been such a pleasure working with them and planning and coordinating this webinar series. If you do have any questions, please do not hesitate to contact any of these organizers. And with that, I will pass it over to you, Brett.
Thanks, Lindsay, and welcome everybody. My name's Brett Williams. I'd like to thank Eric, Helen, all the Fire Science Exchanges for hosting our team for this fueling collaboration. I appreciate the introduction from Lindsay, but we may do a quick round robin just to kind of put names with faces again. Again, my name is Brett Williams. I'm with Region 8 of the Forest Service, the Southern Region. I'm a tech transfer specialist and research liaison for the Southern Region. And I'm also, like Lindsay said, the working group lead for the Eastern Innovation Landscape Network. And we'll talk more about that through our slideshow and through the discussion. So now I'll pass the mic some and just introduce yourself real quick. Start with Mike Gallagher, if you're ready, Mike.
Morning, everybody. I'm Mike Gallagher, Northern Research Station.
And Louise.
Hey everybody, Louise Loudermilk, Southern Research Station in Athens, Georgia. Fuel specialist, TLS specialist, research, co-production, all that good stuff.
Thanks, Louise. Emily.
Hi, as previously said, I'm the fire ecologist for the Southeast region. I work out of Northern Florida. Along with being the TLS coordinator, I'm also an airborne LiDAR technician operating the sensor out of a fixed wing plane.
Emily. Susan, go ahead.
Hi, my name is Susan Pritchard. I'm a fire ecologist with the University of Washington. I'm currently hanging out in my friend's basement during this presentation, so it looks a little funny in the background.
Thanks for joining, Susan. And last but not least, Russ Parsons.
Hi, I'm Russ Parsons. I'm with the Forest Service at the Missoula Fire Sciences Lab, and I'm glad that Susan is reporting from an undisclosed location. So, yeah.
Thanks for that, Russ, and welcome everybody. Yeah, with all the interesting questions, this whole team on a daily basis receives questions, interest about LiDAR and how it can be used for fuels characterization and fire effects or long-term monitoring. And we feel this is a timely topic for fueling collaboration. So really appreciate Helen and Eric asking us to do this. We gave a similar workshop, or we delivered a workshop at the Cohesive Strategy meeting in Atlantic City this past September. And so this was the same group that presented at that workshop, and Eric and Helen thought it was worthwhile to bring us here today. It's a newer technology, LiDAR, and it's mostly in research and development, but becoming operational. And so, like Lindsay said, most fueling collaboration does not have a slideshow, but we felt like it would be beneficial to give some visual context since it's a newer technology and really spur your collective imagination to inform our later discussion. So with that, I will share my screen here. Let's see if I can get it into full screen mode. So that should get you. Am I showing there, Lindsay or somebody? Okay, I'm seeing nods. So just getting my stuff ready here. Okay, so we'll work right into it. The title of our talk is Expanding the Fuels Planning Toolkit, and PLS and 3D fuels, characterization for improved wildland fire decision support. So we'll be talking a little bit more broadly about 3D fuels in addition to terrestrial LiDAR today. And we all know, everybody, most folks on this call probably know that prescribed fire is the most cost-efficient and effective tool for fuels management. But things have changed, and everybody's noticing this if you manage fire, whether it's the weather and climate, the fuels, the urban interface, things are changing, and it seems to be at a more rapid rate day after day. These changes are occurring. And so these changes are increasing the risk of conducting prescribed fires. We ask a lot of our burn bosses and fire managers to go out on the landscape, light a match, and then take responsibility until that fire is out. And so that job is becoming higher risk to me with these changes, whether it's climate change in the form of flash droughts, stronger wind events, a new term I heard the other day, hydrologic whiplash, where you have heavy rains and then long droughts back to back, those sorts of events, or it's invasive species that will affect your fuel complex, whether it's in the southeast Kogan grass or out west cheatgrass or I don't know eucalypts in California, whatever it might be. We're having more novel fuel complexes. And then the WUI is a dynamic and changing environment all the time. New places popping up here and there. Some communities are going through planning and really being thoughtful about how they're building into the interface and into the wildlands, and some aren't. So that's increasing complexity. So even if you're a strong believer in the art of burning, like I am, our current slides as burn bosses, fire managers are becoming stale and outdated in a rapidly changing, no analog future. So we need new tools to adapt to these emerging issues and challenges. Oh, had a little video there, but too late. So what we really need is an expanded toolkit for prescribed fire. Fire management has evolved over time. We've gone from more of a suppression mindset to now more of a fuels management and wildland fire management holistic mindset. Um, so fire science tools need to evolve with our management. The current models and tools that are available for fire behavior analysts and long-term analysts and burn bosses, they were almost wholly developed for fire suppression decision support. Whether it's Behave Plus, for just what's a spot fire going to do on your burn, or a point source or ignition that's going to spread, or mapping into Flam Map and 2D modeling platforms. And they're fast running models, but they're simplified. The fuel models that we use are simplified representations of reality. And fire effects monitoring, we all know it's important, but most of us aren't doing a great job at it. And a lot of that's due to either staff time and capacity, inconsistent methodologies across agencies or within agencies, sampling bias due to who's doing the sampling, and low sample size just due to these other factors not having the time and resources. So one strategy that we're employing in partnership between Forest Service Region 8 and Region 9, the U.S. Fish and Wildlife Service in the Southeast, I believe it's Region 4, and the Department of Defense is the Eastern Innovation Landscape Network. Our vision statement is networked interagency co-production, fostering deliberate, accelerated wildland fire management or wildland fire innovation. We stood up in March of 2023, and the real crux of what we're working to change in the fire research realm is bringing the managers in at the front end, and through what's called co-production or co-development of research of fire science. It ensures that the products and tools that come out of that research or knowledge is usable, and it meets the practitioner's needs, and at the same time collects managers can collect data that the researchers could use to train and validate their models. You can see we have a lot of other interagency partners there on the right. We use living landscapes to test and develop and evaluate these tools. So you can see on the left a lot of our sites in the southeast, and then we have one in the New Jersey Pine Barrens. And this is it's a new paradigm for how we want fire science to move into the future, and TLS is and LiDAR is a big part of that. As we kicked off in March of 2023, got with a lot of the leads at the regional scale or national scale for these agencies, and decided we really want to focus on two suites of tools: 3D fuels characterization and the next generation fire behavior models. So you'll see this hopefully will give you a sense of where LiDAR fits into this bigger suite of tools and this ecosystem. And you'll hear more about some of these tools, but the focus today will be on TLS. And with that, I will hand it over to Louise.
All right, thanks, Brett. So even though I'm technically a researcher, I'm definitely heavily involved with, this application of terrestrial laser scanning for monitoring and for, supporting management as much as possible. And so this really happened about 5 years ago, where a small group of us got together across agencies and said, now that like terrestrial laser scanning, or TLS, we'll say, TLS also stands for, you can think of it as, some people will just say terrestrial LiDAR scanning. That's kind of the same thing. And we got together and said, well, now that we can use a push button instrument, which you'll see here in a couple slides, why can't we use this for monitoring? And so from that kind of spurred the idea, of doing something like this. And so at minimum, you can think of, so this is one individual scan that only takes a few minutes. And I consider it basically you think about a photo point that's been used ever since photography kind of first came out. This is essentially a 3D photo point. At minimum, it's a 3D photo point. And so from this information, you can add that to, your existing sampling protocols, as like another, component of that information. Or if you haven't started monitoring, this could be a way to sort of kickstart that. Information that comes out of the terrestrial laser scan is you can get timber inventory, habitat conditions for ENT species, game species. Next slide. And explicitly map products from the terrestrial laser scan. Just the basic stuff that's mapped from it is you get explicit tree measurements, distribution and sizes. You get canopy cover, which is in the top right there. It's sort of like a bird's eye view of the canopy. So you can get percent cover, percent openness, however you want to think about that. You can remove the trees from the scan, right, and get surface fuel information. You can break up the scan and get different amount of fuels in the canopy and the mid-story ladder fuels, that sort of thing. The idea really is that it's non-bias. So regardless of whether I push the button or somebody else pushes the button on the scanner, the information would be essentially the same thing. So it's consistent, non-bias. It's also efficient. Usually just takes a few minutes to do a scan. We have developed a tiered sampling approach, which is basically, as in any monitoring project, right? Any monitoring program that you have, there's always an initial sort of hump to get over before you sort of continue your monitoring, right? That's always how it is, regardless of what, technology you have or what you want to sample. There's always this sort of hump of getting started. And so that's creating like a sampling design and doing the training for the TLS. And it's learning how to do the scan and how to upload it. There's training resources, and we'll get into that a little bit. Yeah, next slide. Sounds good. Okay. So what also became really evident is, okay, so TLS is great. It captures this 3D structure of this plot scale information, but how does a practitioner or manager actually use the information? And so this was really spearheaded by USGS and the Fish and Wildlife Service, which Emily is heavily involved with, is the Intellimon, that stands for Interagency Ecosystem LiDAR Monitoring Program. You can actually Google this. We can even put in a link. But there's a website that kind of talks about what Intellimon is, and then there's also the interactive viewer. And so this acts as a data online portal where it's where information is uploaded. There's metadata created. It's cross-agency. And all those little green and white and pink dots and different colored dots there that are all over that area, those are plots that are you have the ability to look at your plots or look at other people's plots that are publicly available. You can also have them privately available if there's like data sensitivity issues, that sort of thing. And there's actually we do have sort of in-person training opportunities to do this, and it's usually just a couple days. But there is an online training that's coming out really soon. And we can stay tuned for that. But again, the idea is that it would be a quick place to upload the information, to download it, to have consistent metadata, and you can visualize your data. Okay, next slide. When thinking about, okay, so let's say if we started a monitoring program, we say, okay, we want to start, what are the different roles that might be involved in this monitoring program? And so the first one is, of course, your data collector, right? So there's an example TLS scanner, and so that person would do the data collection and perhaps do some, offloading of the scans. And then from there, you can have the data manager, who's usually the person who's like, maybe help set up the sampling design, right? And again, these don't have to be distinct people. This could be all the same person, or could be, different, one or two people, or however it works out. But it's map creation and plot location. So usually some GIS experience, right? And then there's the data analyst, which is typically more of like a researcher. So, you come to one of us and say, hey, I really think we have this new idea. We thought we could use TLS for this, like, what do you think? Is there a new way to sort of process the information? And then there's of course, the land manager. This is where it really comes down to, right? Is who is the consumer? Who is going to use the information? Who is going to apply the information? For if somebody comes to the forest and said, okay, what are we going to use? What have you been doing on your forest? Can you provide me some feedback on how good your land management is? You said, well, I have this monitoring data. I can provide you this information. So, but I think that's my last slide. So I think we're going to move it over to, oh no, last one is a 3D visualization of the TLS data. So you can bring up your phone and do the QR code there, or here's the website. I think that's already maybe been put in the chat. So this actually came from a co-production product. So a lot of the research that we do is based on, when we get feedback, and says, hey, we would really like to be able to estimate this. So this is a way to look at some of those plots that are in Intellimon, but actually visualize them. So if you use that QR code, you should be able to zoom around in the scan. And also you can look at the table of information that comes from each of the scans. Again, this was all from feedback from says, hey, I just want to be able to see a table of information. Those are all actually DBH values of all the trees in that particular scan. So, okay, I think that might be it for me. All right, Mike.
Thanks, Louise. That was cool to, I just used that QR code and revisited one of my field plots in Washington from over the summer, I think. We just uploaded a bunch of data there. So that's a really cool resource to go look at. So I'm going to talk a little bit about some of the research that we're doing to use these data. And as Louise mentioned, there's kind of a hump to get over, both when you're, for yourselves, when you're starting a monitoring program or refining a monitoring program, as well as scientifically when we develop new tools. And so, one way you could think about this is kind of like we just invented the first new DBH tape in like 130 years. And, over that 130-year arc, there's a whole data science that's been developed to use the data you've been collecting with DBH tapes. And we've got whole subdisciplines of forest statistics and interpretation. And, in the 1990s, maybe it was early 2000s, we came out like the Jenkins equations, and that let us do a whole bunch of new things with all this old data that we'd collected for like 100 years. And so the data that we collected a long time ago with DBH tapes, we're still finding new uses with as we develop new ways to interpret it and new relationships using new tools. So TLS, as Louise said, like we just kind of started doing this in a pretty organized way about 5 years ago. And so maybe that's a little intro to bear with us as scientists. And a lot of what I'm working on right now with Louise and Russ and Susan and Emily is developing some of that background science and to make TLS data more useful and to increase, the different types of things we can predict from it or tell from it. And what's really great is that compared to 130 years ago, the pace of scientific development is just like way faster. And so the things that we're going to be able to do in 5 years are going to like greatly exceed what we could do after like 50 years previously. And so what these pictures are showing are just some of the field work that we're doing to develop those relationships. And TLS, I would think about, it gives us a whole new language to describe forests with, as opposed to just, sticks on the ground or the diameter of a tree or the basal area of all the trees put together. Those are just a couple points in space. And now we can really look at the whole point cloud and get a lot more attributes about the forest structure that we never had before. And some of the things that relate to that are diversity of the flora in the forest. And that's what is going on in the picture on the left here. We're actually down in the Bahamas on that picture on a project where we're actually using this as a method to help them develop a new monitoring program. On the right here, we've got this project where we've been harvesting, like very carefully harvesting shrubs in the understory and drawing relationships between LiDAR and the actual mass of different types of fuel particles. And this builds on research that Louise had worked on down at Fort Stewart previously. And then we're kind of, you learn something and then you also learn what you could have done better. And so now we're all working on this other project to change that. And Susan's going to talk a little bit more about how she's even going in a farther direction with that in a minute. One of the other things that we're working on, though, is just how we can look at change through time with multi-temporal scanning. And my background started off in multispectral remote sensing as a researcher. And there's a lot of multi-temporal imagery that we use, Landsat data, to look at vegetation change. And what's really cool is we have a site that we've been monitoring for just about 5 years now. And what these figures show, each dot represents, each of these plots is a research plot that I have. And the ones on the left are clustered by high severity burning, and the ones on the right are clustered by low severity burning. And this was a management burn to mix things up. It was a fire excluded area. And so the managers wanted to put fire back in there, but make it more heterogeneous while reducing fuel. And so what's cool is that we've been monitoring this, that, the first dot represents the pre-burn amount of fuel. And I'm sorry I cut the axes off, but that's time 1. And then each dot after that represents burned and different points in recovery. And what's cool is that you can see like a huge drop in the high severity places. We burn things so that all the pine needles are gone when we do that in the New Jersey pine barrens, and then they all grow right back because our trees do that. But the low severity sites are interesting because they had a much more subtle initial impact, and then they just kind of kept having this low decrease for another year. And that was as all like the dead shrubs and stuff started to fall down and the fuel kept changing in a negative direction. But in the high severity sites, that was all consumed initially anyway. And so what's neat is that we can watch these different trajectories play out through time with different levels of treatment. And this is across the whole vertical strata of the forest, but we could do this for the shrub layer and the mid-story and the canopy. And when we look at it in that way, we could kind of define like a fingerprint of our management. And, we could use that to define the fingerprint of maybe habitat for a species, or what successful fuel reduction looks like and how long it might last for to defend when we have to come back in and manage again. This is just a picture of what that data looks like over time. This is one of the plots, and you can see how we could split it up by shrubs, trees, understory, and we can look at that post-fire, change, and then how that starts to come back with time after fire. Next slide, Brett. And so this again just has that broken out by different forest strata, and we're looking at how this is aggregated all the plots in that burn. We're looking at how these trends are playing out through time. So this is just a way that you could describe to your supervisors or your stakeholders or in your budget what you did and why you need more money to keep doing it. And then this is just what all the plots look like from that one burn. And I'll just point out also that each of these points, took a little while to walk to, but it only took 30 seconds. Each one of those dots represents 30 seconds of effort in the field to scan. And so, my crew can get through that in like less than a day. They go out for less than a day each year and collect a bunch of data, and that's that. And so it's a nice, quick way to work. I also just want to highlight some new work that Louise published, and I'm sorry that the reference there at the bottom I didn't see the color there, but one of our collaborators, Juan Casarina at Los Alamos, works with Louise and I and some of the others on this call. And one of the questions that we've been getting is how to use ALS and TLS together. And that's not the full scope of this call, but I just want to point out that there's this great new paper that Louise is on that came out like a week ago. And it looks at aligning TLS scans with ALS data. And this is like a really nice innovation, I think, that is going to advance how we use these data. So with that, I'll pass the mic.
Yeah, so I will be talking about how it can be used for adaptive land management. So currently there are actually over 200 raw metrics outputted from IntelliMon, but which of those are actually relevant for informing fuels management? So we made a correlation matrix to identify which variables are strong indicators and can be used to evaluate effects. Then models can be built using those with the strongest correlation. So these are some examples of models that data analysts can build. And the models on the left are of the variables with the strongest correlation at a refuge in Georgia. And the pre is a scan the summer before treatment, and then they burned in the spring, and then they scanned that summer after. So these scans can just quickly and easily quantify the change in fuels after the burn, and it can be used to assess effectiveness. So the variables with the asterisk were statistically significantly changed. So they decreased the field bed depth, they increased the bunch grass cover, but depending on their objectives, they might need a different approach to reduce the desired result for that woody shrub cover. On the right are linear models showing the change in fuel related to time since burn from a refuge in northern Florida. So the x-axis is the month since burned, and then the y is either a percentage or a centimeter height. And these quantify the fuel's response over time so that land managers know how frequently they need to burn to keep those metrics within desirable conditions. So what is kind of that threshold for maintaining fuels? Brett. So looking at thresholds, these models highlight how different fuel conditions change over time, spatially at different refuges in the Southeast. So the red areas indicate significant rates of growth and the thresholds of the system. It helps to quantify the rate of change, the rate of growth in different fuel types, and it shows how that impacts your management. So when do we need to treat before growth happens and it becomes unmanageable? So if we look at St. Mark's in the bottom right corner, that looks to be about 60 centimeters. Next slide. Then we are able to spatially depict the average fuel bed depth from the TLS data of the different management units and colorize those fuel bed thresholds. So this is a map showing which units are above and below that 60 centimeters. And this is really helpful for prioritization and classifying management goals. And we can give this to the land managers and they'll know which units that 60 centimeters is actually relevant for. So is that 60 centimeters of shrub or is that 60 centimeters of marsh grass? Next slide. Thanks. And within fish and wildlife, a critical species impact when, where, and how we manage land. And a critical species that a refuge was established to manage for is Mississippi sandhill crane. So we collected TLS data at this refuge, and we were really interested in comparing the tracking data of the cranes with the habitat results from TLS. So data analysts began by modeling 4 different TLS metrics, and the variables were then broken down into intervals, and each interval was given a score out of 10 based upon crane visitation frequency. So the areas that the cranes were visiting the most got a score of 10, and those areas that visited not at all got a score of 0. And then a habitat suitability map was made for each of those TLS metrics, and then we added them all together for out of 40, based upon that metric and the visitation. So overall, the refuge got a score of 38 out of 40, which is very good, showing that the restoration is very effective for restoring that crane habitat. And we will be applying those ideal habitat metrics to a nearby refuge that is up for crane translocation so that they can implement those same management treatments to get that habitat structure ideal for the cranes. And that is the end of my section.
Thanks, Emily. Over to Russ.
All right. Howdy, folks. I'm Russ Parsons from the Fire Sciences Lab in Missoula, Montana. Really excited to be here today and so excited about the new technology that all our partners are talking about here. Okay, so what I'm going to talk about a little bit is how some of this kind of 3D data can fit into a bigger, an expanded toolbox for fuel management. So if you could click for me there, Brett. Yeah, so we've been developing this thing called Fast Fuels, which is a platform that captures 3D data and provides inputs to 3D fire models. And one of the important things that we're trying to think of here is basically expanding our toolbox. We're not trying to replace the old tools. We're trying to give you more tools to work with. So particularly focusing on applications of prescribed fire and fuel treatments. Next slide, please. So we have this system that models fuels in 3D called Fast Fuels. This is an example of like I think about a 40-acre chunk of land. You can see the individual trees are comprised of 3D voxels, and each one of those voxels has all the attributes needed to run the new next generation 3D fire models. Let's go ahead and go on to the next slide here. So when we talk about Fast Fuels, we often think of it as a superhighway connecting fuels data to fire models. So one of the things we're committing to with Fast Fuels is to provide data for all of the models and to provide a pathway by which real fuels data can get into those models. So it enables those models to be compared against each other with the same fuels inputs. Now, we have Fast Fuels data for the entire lower 48 at 1 meter voxels, but you might be wondering, how did we get that? Right now, it's based on a FIA imputation called tree map, in which FIA data are imputed to other areas based on landscape similarity. But if you could click, Brett. So again, going back to the idea that Fast Fuels is a superhighway connecting fuels data with fire models, on-ramps are data assimilation pathways in which that kind of default data that we're leveraging the FIA data to enable us to do this across the country, but is not as specific to that spot. You can update that and get more appropriate site-specific data in there. Next slide, please. Or yeah, there we go. So it's basically like you've got a system, you start out with some default data that's pretty good, but then you have a way to get it better. So this is an example of that from Montana. This is a unit in that is owned by the Confederated Salish and Kootenai tribes. One more click there. Let's just jump to the next slide there. So the previous slide showed imagery of this unit. And you can see this is what it looks like when it's brought into Fast Fuels. So we took the airborne LiDAR scanning data from that unit, and we used our airborne LiDAR scanning on-ramp to bring the actual tree data from that unit into this system. We're also, if you look at the variability in the surface fuels, there's also a model developed at Los Alamos National Lab that couples the overstory fuels with the understory fuels there. Okay, next slide, please. So with that 3D data in Fast Fuels, we can then run very sophisticated 3D fire models through that unit with multiple 3D fire models. In this case, Quick Fire, developed at the Los Alamos National Lab and with the Southern Research Station of the Forest Service. And you can see that in that we have multiple igniters moving across the unit and kind of going back and forth as we tend to do. And you might notice that we're getting some escapes out there on the other side of the unit. Now, in the real world, you'd probably call somebody on the radio and say, hey, stop igniting. We got some slop over here. But these, you have to remember, are just little computer pixels, so they don't know. But the important thing about this is that it actually gives you a whole new realm of exploring the potential for slop over in prescribed fire events. So what we're thinking is that this whole setup is going to enable us to analyze prescribed fires, fuel treatments, explore our options better, and ultimately get at a more focused site-specific risk assessment. So that's it for me.
Thanks, Russ. Wrap it up with Susan.
Awesome. Hi, all. So I'm going to just give you a few slides on a very new project that, much like Mike said, I feel like we're more in the research and development. It's exciting to see LiDAR metrics immediately be put into action for monitoring, as Louise and Emily were talking about. Whereas this project called Fuels Craft, which should sound a little bit like Minecraft, is much more in the development phase. I have a lot of collaborators. Some of them are Russ Parsons and Mike Gallagher, Nick Skoronsky, and then University of Florida is also really involved. And so with Fuelscraft, what we've been trying to think about is how to harness terrestrial laser scanning along with some really fine scale object scanning. What we're seeing here is some oak leaves scanned by literally the same kind of scanner as we now get, thankfully, in our dental appointments. Instead of actually having those awful impressions, we now have scanning of our teeth in a digital 3D model. Same thing is now possible for objects, as we call them, within these fuel beds. And so briefly, I just wanted to, if you could advance slide, Brett, that would be great. Wanted to talk about some of the context for me as a fire ecologist who's spent my career on prescribed fire decision support. So on the left, on the bottom left, we have basically just a land fire scene. So 30-meter pixels of different fuel beds. So these would be FCCS fuel beds mapped. I don't have a legend here. I just wanted to kind of share that in the past, what we've really done is use Landsat TM imagery to classify vegetation and then model fuels, both the surface fuels as well as the canopy fuels for prescribed fire decision support, whether that's for fire behavior or smoke. Someone said not seeing the slide, still sharing Brett's screen. I think we're okay. Is everyone else seeing these slides? Sorry about that for that person.
I can see them.
Okay, great. And so, there we go. I'm so glad, Cameron. So up above, we have Russ and teams work with Fast Fuels, where basically now we're moving into this awesome superhighway of trees, where we can actually have tree lists informed by FIA plots to model trees or actually get those from airborne LiDAR. So a huge advancement on the canopy. In the middle slide, I'm showing image of southern pine forest, and sure enough, like we can see trees really well from airborne lidar, but the fire, as you'll note, is on the surface, which gets really tricky. So we've seen some excellent on the ground monitoring plots that inform mapping of understory fuels, but we're not going to have those everywhere. And so the understory fuels are still probably needing to be modeled. So we had the land fire approach to 30-meter pixels. Now we're moving into an awesome new world where we have a lot of resources to map canopy fuels, but how do we actually create wall-to-wall understory fuels? Next slide, please. So within our fuels craft design, we're kind of well underway on this, but basically we're building on the very left column here, scanned objects. So we can actually have objects characterized in 3D models for especially shrubs, but also components of litter. And we're actually truly building synthetic representations of these fuels so that we have 3D models of what can burn in wildfires. And then as we've collected a lot of data sets, and we'll definitely be collaborating with Louise and others as well, we'd like to make use of plot data sets to move into machine learning algorithms to place objects probabilistically in understories based on overstory, and also time since fire in different treatment under scenarios. And so we're really right now in this space of trying to be on-ramps for fast fuels for understory fuels. We can either go from direct measures from TLS, shrub height models is a really good example, or probabilistic synthetic or simulated fuel beds to map for managers. So stay tuned. I wanted to just do a few slides as teaser, but I'd love to come back and talk about where we get. So thanks, Brett.
I really appreciate it, Susan, and all the panelists there. And before we start our discussion, I know that was a little bit of a long slideshow, but I hope that you all got more context and got some imagination spurred there, and that'll inform our conversation. I just wanted to show this slide one more time to kind of put it all into perspective. You heard a lot about TLS, some about fast fuels, a little bit about quickfire and these other models. And this is kind of that ecosystem suite of tools. It's in development. Some of these, the right-hand column here with fire effects, smoke modeling, ecosystem modeling, that's in development, but that's ultimately where we want to go, is to be able to use 3D fuel models, next generation 3D fuels, next generation fire behavior models to predict fire effects, smoke modeling, which there's a quick smoke application and others in development, and then ultimately ecosystem modeling and how we can look at regimes or disturbances or change over time. So I'm going to stop sharing now and dive into our discussion. Do a few things here to get the right questions up for myself. So we're going to kind of explore, we really appreciate everybody's questions that came in, and I did my best to group them into kind of topic areas. So we're going to explore a whole range of topics here, from how TLS can be used and useful for monitoring, for fuels characterization and fuels treatment effectiveness, adaptive management. We'll also a little bit later on get into kind of cost training. What does it take to get there and get started? Data processing, data management, and we'll kind of end up on where we see it going into the future. But to kick things off, I think we'll start with monitoring, because that's where I get a lot of questions day to day. And so I was going to just go open it up, what folks see on the panel as pros and cons of TLS versus kind of either current or traditional methods of monitoring. And I know we touched on this in our presentations, but anybody want to recap that for us real quick? Maybe Louise, since I think you
Sure.
touched on that.
So yeah, I mean, just from conversations, that we've had for, like I said, at least the past 5 years or longer, is, you know, people struggle to implement, or consistently use monitoring programs for various reasons, right? Some of them we can help with, some of them we can't. And part of the issue is, there's many issues, but it's either, inconsistent information. The information maybe isn't accessible, right? It's kind of sitting in a filing cabinet, right? Or there's a lot of or they're done differently between sites or between organizations, between agencies, right? There's huge differences between agencies on how information is collected. There's also just data quality issues, right? Like it's very dependent on how well that person is trained, to collect the information and how much the effort they're willing to put in to collect good information. And all those kind of like human, biases that are intentional or unintentional, right? And so I think that's one of the things that really spurred us along, right, with kind of doing something like this is, so with TLS you at least cover some of those bases, right? You cover consistency, you can cover bias, to a large degree. It's a lot quicker, right? You're collecting millions of points in a minute. And also the idea with sort of the Entombment system is that, and again, it's, we purposefully drove this, cross-agency effort, and so the idea was, okay, let's start with the most basic thing. How do we use a single scan, and get information from it? And from there, like I saw a little bit, I just kind of browsed a little bit on someone said something about like multiple scans, and that's actually something that we're working on right now, right? It's part of several of our projects. Some of the work that Juan Castorena is doing is how do we merge multiple scans together in those areas where you have the difficulty of like really dense vegetation, where your accuracy is going to get a lot lower, that sort of thing. So, I think we can get there, right? This is kind of the first big step, in kind of going in the right direction. So I'm going to stop there. Maybe let
Hey,
somebody else.
Louise, I kind of want to build on what you were saying there too about the scans and the multiple scans, and a lot of this technology really came out first to be used in the built environment, in warehouses and in architecture, or even with the work that Susan's doing with scanning fine scale plant pieces, to evaluate parts of machinery and things that are difficult to build or no longer in production. But taking those tools from the built environment where things follow, rules that we came up with to build them, out to the forest. The forest is like entropy. It's just such a messier environment, and so you might think, why is it hard to like align two scans together? Well, when I don't know, you got a building that's got 4 flat sides, it's not hard. But when you've got a forest that's got a million irregular sides, it is a much more daunting task, and requires a lot of different, a different process that nobody's had to worry about in the built environment, really, I think. So just kind of wanted to add that there as why we're doing that a little bit.
And I'll pull it back to pros and cons. So some other issues within the federal service is having the capacity of staff to get out in the field, having the resources, having the time. And so this training takes 2 to 3 days to completely understand, start to finish, the field protocol. Anyone can do it regardless of education, of background. The plots themselves to that initial baseline take 45 minutes to an hour, but then the concurrent years take less than 10 minutes to do a scan. A single person can go out and do it alone. So it really helps with that factor because people just don't have the time and resources, and it gets that whole big picture, right? So it's not a forester going out and a biologist going out to the same stand. Anyone can go out, press a button, and then that data benefits everybody. And they can easily access it on Entombment. It's not locked and unorganized in some file that then people leave and no one knows what happened to that data, how it was done. Also, the scans are able to be reprocessed year after year as our analysis improves. So right now, you might be looking back at data sheets from 10 years ago and wish that those people had collected different information. You can't read their handwriting. You know for sure that technician was not doing a great job. That's no longer a problem. We can just reprocess those scans over and over. And, you know, as Louise was talking about too, it removes all that human error and all that human bias. So you might have someone who wasn't trained super well coming in and doing it, or even if they do really care about the quality of that data, I see a plot differently than Louise sees a plot. And so it just removes all of that, even if you are really, you do care about the integrity of that data. It's just a press of a button, anyone can do it, and it's the scan collects the data with equal precision each time.
So Emily, you brought up the first year. There is some additional the largest investment is in the first few years or the first baseline scans you take, and kind of relates to a little bit to Luis talked about getting over that initial hump. Very much applies to LiDAR because a lot of the investment is up front. Can somebody speak to, maybe starting with you, Emily? The Luis talked about the tiers of sampling, but well, kind of how the tiers work and why you need to do so much investment on that first round of scans. Maybe we can start with you and move to others, but yeah.
Yeah. So there's different tiers. So the tier 2 is that initial baseline plot. And like I said, it takes 45 minutes to an hour, and it takes a little bit of past sampling methods and combines them all up. There's a point intercept sampling. There's of course woody debris sampling. We collect overstory data. We measure the fuel bed height, litter depth, duff depth. And that's kind of the gist of it. And then that is training data against the AI. So then against the machine learning and against the point cloud. So you use machine learning to assess that based upon that training data. And then the tier 1, that takes, like I said, less than 10 minutes. It's just a scan. And we also collect the tree prism data. I'm sorry. We also collect a basal area then as well. And Louise does tier 3s, we kind of call them. And other people do tier 3s as well. But she collects a biomass sampling too. But Louise, correct me if I'm wrong. So that's our tiers, and it's just you collect that for the training data. And we hire intern crews to do those first ones, and then refuge staff do the concurrent scanning after that. And we do scanning, it depends on your objectives, but we do scanning the same time of year after year, because we're just doing long-term monitoring. So everyone kind of asks, well, when do you scan? And it's, well, what do you want? Do you want those first order? Do you want those second order? We're kind of just looking for the long-term habitat structure change. So we do after treatment. And I think that was all your points you asked me.
No, that's great. I don't know if Louise or Mike or Susan want to follow up with kind of building relationships and training the point cloud data.
Yeah. So Emily is using a framework to for their program in Fish and Wildlife that involves these 3 tiers, and we've defined those 3 tiers as like a really sophisticated plot with all these other measurements besides just the scan, and then like the last tier is the easiest, which is just go scan and don't do anything else. And so she explained how those are training data and testing data that enable that last, that's that investment that allows you to just go out and press the button without having to train it anymore. But there's other, it doesn't have to be the same. We came up with a simple smattering of things that are very general things that a lot of people like to know, that are basic monitoring things for fire. But you could go out and have your own set of criteria and train models in your own program with different criteria. Maybe it's Kirtland warbler counts or Indiana bat habitat. And so, you have a way to evaluate that, and that could be your training criteria to see if your plots are falling into the, meeting your objectives or not, or if they need management, and defining that. And so, there's, I think that I feel like we get asked a lot, like, we're just going to monitor something, tell us what to monitor. And that's a hard thing, because you could literally monitor. Emily and I were talking about how it's kind of like monitoring your receipts, you know, like you probably got some friend who's like, you got to save every receipt. And like, you know, and it's like saying like, well, one line on one receipt, like, sure, told you that you bought toothpaste in February, but like, is that useful? Like, maybe not, unless like maybe if you're working for the VA and you're in charge of like a taxpayer spending to help people, then maybe it is, and maybe it justifies why you need another budget and how you met your objective. On the scale of like an individual, like I could do that, but I also just know that I have toothpaste, so I don't like that monitoring is not helpful. And so like the questions that you ask of this really, and the amount of monitoring you do or the amount of money you invest in should really answer like your program's objectives. And if maybe, you know, if monitoring is not your objective, or if you can just go look outside and say like, there it is, like we cut a tree and there's the stump, maybe that's good enough. And so just think about, I think it's just a good way to think about it, that, you know, there's a lot of opportunity to monitor, but you know, just like there's a lot of opportunity to like, you know, hang on to every receipt and lots of shoe boxes. Like if that's not really your objective, then why do it? And just think about the scale that you need to do to meet your objectives.
I'd like to piggyback off that too. And maybe that one receipt with that one tube of toothpaste, you look at that one receipt and you're like, oh, that means nothing to me. But then you start looking at the trends and maybe you're buying toothpaste every 2 weeks. You're like, well, maybe that's more than I want to, or just vice versa. And so having that receipt, maybe you don't think that it's important. Having that scan, you don't think that it's important until someone else comes and asks you about your funding, about why you were doing what you were doing. And then it's really important to have that data to back that up, or that data to assess, maybe we need a budget more for toothpaste, or maybe we need to use less toothpaste. Just something simple like that. It's just more data. That's how we use it to assess trends over time.
I love the analogy. It's great.
I'm
Susan,
gonna just chime in really quickly if I could. I love this. I'm so excited about Intellimon, and I absolutely agree with how consistent the measures can be, and how finally in ecology we have some metrics that are not going to be swayed by different field crews. That's incredible. I also wanted to just say that I really appreciate this idea of what is the use case. And so right now, especially with terrestrial laser scanning, understory structures such as especially shrubs are well characterized. If we want actually these plots to inform fire hazard, and that litter beds are really important, I was just going to add that sometimes those are occluded. Sometimes they're very hard to actually pick up with terrestrial laser scanning, even though they might be the most important thing to measure in terms of potential fire behavior. And so I think that there will be some cases where, you know, you could talk about tier 3 sampling or just additional sampling to build on what you're actually monitoring.
You hit on a few topics there, and because of our slideshow went a little long, limited on time, so I'm going to skip ahead real quick. Let's talk about kind of the limitations for TLS as far as let's talk vegetation density. Maybe what are the limitations, and how do we overcome those? I know Louise mentioned one that she can maybe recap, but anybody want to kick us off on vegetation density?
Yeah, I think all of us could definitely talk about that one. You know, it's you know, Susan just brought up a really good one with the litter beds. That's a reason why we actually collect it in the field, right? Because it is so critical, and a lot of people ask about it, right? And how does it relate to litter depth, right? And a lot of people have different definitions of what litter is, but we won't get into that. But you know, there's you know, we kind of bounce around the term of occlusion, which basically means like, so if the laser isn't able to see it, like if you can't visually see it when you're standing at the center of the plot, neither is the scan, right? So if there's a really large tree, you know, the sort of everything behind that tree is going to be blocked, right? It's like a flashlight, right? And so within the metrics, right, which is generally like the measurements that come out of the terrestrial laser scan, Like it within Intellimon, occlusion is sort of incorporated into a lot of those metrics. Is like how occlusion sort of restrict the size of the area that we're actually measuring. All those things are sort of incorporated. We've thought a lot about that. But some things to overcome is to think like just because we can't see it doesn't mean we can't make predictions about it, right? And so that's a little bit more of like a research kind of thing, but that's something that I think a lot of us here are really interested in is like, okay, if we know it's really dense, we've got to scan the middle of it, and it's like looking at a wall of vegetation, that's still telling us something, right? And we can make predictions about a density that's in a larger area beyond that, right? And so that's for us to deal with, right? And that's something that we can apply, but we would love feedback from you guys is, what are some of your thoughts on that? Another thing is what we were talking about earlier is sort of like combining scans, right? That's definitely on the horizon, something we've got funded projects to work on. Let's see, I talked a lot about occlusion there. So it is, somebody mentioned something about structure. So basically, yes, TLS is measuring structure in any way. And one thing it's like a lifelong career thing is like, how do we stop thinking? Not really stop thinking, but in addition to like basal area, like Mike mentioned earlier, how can we create new cool ways of measuring the forest that's intuitive to anybody who hears it in our field of research, right? And I think this new way of being able to look at actually measuring the structure, like truly measuring the fine scale structure of a landscape or of a plot, how do we sort of move forward? I think it's like a really cool new even way of thinking about it for management. Anyway, sorry, I'm going down a rabbit hole. If anybody else wants to chime in on limitations, I know I kind of stopped right there, but there's more.
I'll throw out a
Russ.
word or two.
Yeah.
Yeah, so I think it's important to remember that this TLS stuff is really just the tip of the iceberg. So if you go out there right now and you take a scan, that data can then be used with all the new algorithms that we develop going down the path. Okay, so like it is, yeah, it's capturing structure. We've never really been able to talk about structure before. So we're having to develop new algorithms to talk about what are we seeing in the structure, right? Like, so you think about it, like the concept of fuel continuity is something that we intuitively understand as fire managers, and we think about it a lot when we're, walking through there with a drip torch. But we've never really had a way to capture it until now. But we don't even have great metrics for it yet. So I think that importance here is, like Mike was saying, when they invented the D-tape, okay, they didn't know about allometric equations for biomass for trees. Or maybe they did. I can't remember. I could go back in time or somebody could Google it. But think of all the science that came from those measurements, right? And right now we're just in this early kind of pioneering stage where now we actually have these gadgets that capture the 3D structure in insane detail. In fact, I would propose that TLS could actually be an acronym for totally ludicrous scanning. But yeah, I mean, you're getting this tremendous data, and the algorithms that are in Intellimon right now are, even though they're incredibly sophisticated, they are themselves just the tip of the iceberg of what we'll be able to do with this data going forward. So, yeah, there's the other thing that's interesting about these scans is not only are they getting structure, but they're getting the RGB color colors tagged to those points. And you can see from some of those scans that like you get the sky will bleed into a tree. So you get some, the sky's the background. So sometimes it'll pick up blue sky or clouds or whatever. So you have blue or gray, tinges to your thing. But there's portions of these scans where the colors are fairly legit. And that itself is additional information. Like we had a paper in 2022 where using similar point clouds from drones, we mapped fire effects in 3D. So anyway, the other thing that I think it's important to understand is also that these different point clouds are very complementary in the data they provide. So ALS, airborne LiDAR scanning, is capturing the big picture people do flights of, that costs millions of dollars and capture thousands of acres. Okay. It's seeing the tops of the trees really well, and it doesn't see the understory very well, typically, unless you have really high point density. Okay. And then TLS is this analog to like what we do with a plot. It's like a super plot, right? And the ease of using this gadget to just go out there and capture all this information is unbelievable. But there's a kind of a glue scale between there, which is drones, because drones can be flown on a project area. They get data through photogrammetric approaches that's similar to LiDAR, and also provide high resolution imagery that enables you to look at the surface fuel. So I think all of these point cloud data sets are really importantly synergistic in enabling us to get there. And again, all of these things are kind of new and expanding at the same time. So I think of it as a golden age for fuels measurements.
I know we need to move on, but I'm going to just say one more thing. I loved what you said, Russ. And there's still never going to be a substitute for some on the ground measures. So coming back again to litter layer, fine wood, those are things that these sensors don't pick up very well. And so I'm pretty excited, I know others are too here, about the co-production that we can do with on the ground practitioners and fuels crews to actually measure some of these fuel variables to be able to then model better what the sensors can't pick up.
Oh, this is great. You're right, though. We're running short on time, so I'm going to move past a few things, but we started talking fuels there. So any other thoughts or discussion on how 3D fuels, whether it's TLS, the whole suite of tools there, can be used for, or how can it improve upon our ability to monitor fuel treatment effectiveness, or plan fuel treatments, or plan prescribed fires, whatever that might be. But we were talking monitoring. Maybe we can move into like more of the fuel characterization and use. I know Russ kind of started that, but
Yeah, one thing I'll say really quick is, again, from getting feedback from practitioners and managers, we actually implemented into the IntelliMon system. So this is what Emily was talking about, was like, so those scans that we already uploaded, right, we can recalculate those, right, and like add new measurements to them, right? And so one thing that we recently implemented was this. People said, well, can I just get, if I did a pre and post scan in an area, scans in an area of an area that I did field treatments, right, where I did some thinning, can I get some estimate of how much that changed? And so we've got this volume estimate now. We have volume of the canopy, mid-story, surface fuels, and so you can get volume change out of those two plots that you did pre and post. So I just wanted to throw that out there, that's something we got going on, and we're going to just continue expanding on that idea, right? And applying mass to that, and yeah.
Yeah, that was my follow-up, is what's the challenge with applying mass to that? And I get a lot of questions about, hey, like post Hurricane Helene, how do I get a quick estimate of the biomass change on my landscape? And I always have to explain it's a little more complicated, but maybe you could elaborate on why that's complicated, or what we need to do to get there.
It's complicated because mass varies a lot more than structure, right? You've got coarser debris that could have the same amount of volume space as like another area of the structure. So, yeah, I mean, I'll let
I can jump into that a little bit.
Yeah, please. Yeah.
So, yeah, one of the interesting things about point clouds is that they really capture the structure. Okay, but it takes a lot of work, and you're seeing some of this already, like in the some of the new work that's separating out the point cloud to foliage, shrubs, etc. Okay, but point clouds fundamentally tell you where things are, but not what they are. So you have to do additional work to figure out what they are. Okay, and so kind of with fast fuels, what we do is we use allometric equations to get to biomass, and then we distribute it within the tree crown. Okay, so fundamentally, when we go out and collect a tree diameter, it's given us a pretty important insight about how much stuff is on that tree. And it's because if you go back to all of the pipe theory and all that, the amount of stuff that can grow on that tree is limited by how much water can go through it. So the diameter of that tree is a pretty important predictor of all the stuff above it and below it. Yeah, generally speaking, you're not going to go directly from point clouds to mass quantities without some additional modeling. And I think a lot of the work that's being done is teasing out how to separate the different components, and the clipping and fine scale work that Louise and Susan and Mike have been doing with their teams is really fundamental to quantifying those things and building those predictive relationships that get back to when you take the scan, now it knows what's there and how much stuff is there.
No, that's great. Great, Russ. Yeah, I was just looking through the chat. I was going to go in a little bit into cost and training, but I think with the, well, let's do this. I think, Susan, you mentioned something about risk or kind of hazard mapping and risk management. I haven't, what's going on in that space with TLS and 3D fuels, or is there much?
Yeah, I'd love to hear from the rest of the group too. But I will say that there was a question in the chat that I really liked, and it was about what about complementary remote sensing such as SAR? So,
Okay, go for
oh
that.
my gosh, the synthetic aperture radar, is that right? I think it is. Yeah. It's a little early on the West Coast. But anyway, so Louise mentioned that TLS is particularly great at mapping the structure of fuels. Like, what an amazing achievement that we now have high fidelity, high resolution measurements of fuel height and where fuels are in 3D space. The what are a big question, but one of the opportunities I think that we especially have for our fire hazard mapping is that we now have the template of fuels. So if we think about that structural template, then we can start either measuring or modeling the fuel moisture and when those fuels come online in different seasons and how those interact with fire. And so I'm fixated, and I will remain so, with the Fuelscraft project about informing litter layers and fine wood that really drive surface fire behavior. Right now, some of that mapping of the structure and biomass of those fuels is modeling, but I think it's very exciting to move into the next space of, well, can we do some other measures of seasonal fuel moisture to drape on top of that to be dynamic with these structural maps. So we've got this structure, and then dynamically over seasons, these fuels come online and are more available for assessing fire hazard throughout seasons and throughout drought events even.
Well, thanks for that, Susan. Anyone want to add to that, or we can move on?
Yeah, I think that where we're headed, we're going to continue to see increasing sophistication and depth of new algorithms for mapping the structure and the characteristics of fuels. And as those get connected to the moisture dynamics and everything, we're going to have a better view of fuels than we've ever had. And I think it's a really exciting time also because now we finally have 3D fire models that can handle that data. One of the interesting challenges about LiDAR is that a LiDAR has always been ahead of what the application's for. So typically, like you think about when we map forests, we're looking at national scale data like land fire. If you had LiDAR data, literally the first thing you would do describing that forest canopy data would be to throw out 99.9% of the detail because none of the systems could use that information. So it's a really exciting time because the modeling tools are catching up to the data, and the data is also expanding. So it's a cool time to be in this arena.
So we haven't really touched on, we've talked about Intellimon, and I can't remember if it was mentioned, but there were a lot of questions about who has access to Intellimon and the training and that whole ecosystem. And And so I don't know, Emily, if you want to speak to that, or we can maybe have others, but kind of where we are in the progression of Intellimon and who's involved and who can access. There were a lot of questions about, hey, can private landowners get involved, or states or NGOs, or so maybe you could speak to that best you can.
There's, I can speak to that there's currently a steering committee being organized to help inform like the private landowner side of things and the state organizations. If you go to our Intellimon site, you can see the list of the organizations using the public layer. There's also a private layer for data sensitive organizations, BIA, DoD. And so anyone can get into this open data and download that raw data, but it doesn't really mean a whole lot if you don't have that training data associated with it. So that's why it's not really a security concern, because it's just a whole bunch of numbers if you don't have that training data to tell you what it actually means. Training wise, we have a field training coming. It sounds silly. We have an online training for the field portion that is about to be released and public for those who have access to that training. And then we are developing a data manager course to help manage the maps and the TLS data, the different point clouds, and that training data collected. And then next will be a data analyst course. So how can we actually build models from the Intellimon data?
That's great. Appreciate that. Hopefully it answered most of the questions folks had, but reach out to the contacts on the Intellimon site or to any of us on this call if you have follow up on that. I think we'll kind of get into futuring with the last 8 minutes we have here. And you've already all talked about this, but I'll just open up with a few questions. Where do you see TLS and ALS, airborne LiDAR, terrestrial LiDAR in 2 to 5 years? Or maybe let's just say 2 years, because 5 is like Mike said, that's like 50, last decade or last century or whatever. But 2 years, where do you see TLS, ALS technology based on the rate of kind of development and research right now? Or can you imagine?
So, well, I'll say one thing I think that's going to start changing, and I'll circle back to something I said before. I started my remote sensing career with Landsat data, which, if you're not familiar with it, it's multispectral satellite data that the first Landsat came out, I think, in 1972, and that you can get this multispectral data back to 1984 now. A lot of the university graduate programs and remote sensing programs are still like, it's like an even aged forest that all seeded in at the same time of remote sensing programs, where they're all still, they seeded in when Landsat started. And that was really when remote sensing, I would say, kind of transformed from air photo interpretation into like, computers were starting at the same time. But a lot of those programs, in my observation, have not really fully embraced LiDAR data. They've used it for things like, analyzing ice sheets melting or beaches eroding, which is relatively simple compared to what we're trying to do, where you've got a pretty flat surface or basically an undulating surface changing. We're trying to look at this three-dimensional structure as a porous material changing. And so I really think in the next couple of years, as these programs start to change, I think that we're going to get more investment in LiDAR in some of those programs. And I think that's really going to accelerate the pace of innovation. And so I would almost say that's been a limitation in my experience. Even finding, we all have a story about how we couldn't find a graduate student with the right skill set to use LiDAR data, because there aren't that many programs in forestry and ecology producing them. But I think that's slowly changing. So that's one innovation or one change I'm excited about.
Let me add to that briefly here. I can remember not too long ago when phones had this cord and the thing plugged into the wall. Okay. And then they came up with the little text phones, flip phones. And now we have these crazy phones that do everything. Okay. Well, all of these technology things are advancing so rapidly that it's really hard to keep up with them. But the potential that they add is tremendous. Okay, so like LiDAR, I predict LiDAR is going to become incredibly commonplace. And in fact, if you buy a car right now, it typically has 6 LiDARs on it. Okay, and many of the new phones have LiDARs on them. Okay, and a process that we use with drone imagery to produce point clouds photogrammetrically called structure from motion is now widely used by insurance agents. If they show up to look at a car accident, they just snap a bunch of pictures of the accident and they produce a 3D model that shows that it was the left bumper, not the right side that got hit. And so far, you were lying, buddy, you were lying. So in fact, this technology is changing around us every minute. And in fact, we have a project where we're using the LiDAR and the cameras on a tablet to enhance plot measurements on in conjunction with the TLS. So there's a rapidly developing envelope of new technology, and it's only going to become more integrated and part of our daily lives to the point that we don't even notice it anymore. But meanwhile, the science it's such an exciting time because we have more data and more complementary data sources that we can bring together, and also all of this AI and all that, which means that you can learn from the data sets we had that would be otherwise very hard to do. So I'm going to stop blathering.
Yeah, Russ, you made me think about how much things have changed since we all started on this particular line of research. Like we all had done some stuff with probably some airborne remote sensing before 2018, and a couple papers, and then around 2018, this relatively inexpensive LiDAR came out that we began dabbling with, and nobody had done plots like this before that. Nobody had done monitoring like this before that, and we started playing with these tools. And trying to think about what to do with the data and how it worked. And, now we have an interagency online, portal to archive your data and to process it. And we have this coast to coast group of scientists working on from the particle size to the tree size to the landscape. Everybody's working in tandem on all these different facets of it to bring it forward. Just the changes and there's a guy, Kevin Hires, who's not here on this call, but I think he really brought a lot of us together and had a lot of early vision for how this would all work like this. And in the last 4 or 5 years, it's just crazy how sometimes we get stuck thinking we're stuck trying to update the firmware, and we're like, man, this is is this ever going to get anywhere? But if you really look back at how far this has come just in the past 5 years, it's been revolutionary.
Quickly say I'd love to hear Emily and Louise have some final remarks too, but very quickly, I think that the future in a couple, 3 years will also be through collaborations with computer scientists. And so as we're moving into better LiDAR, this modeling aspect and the ability to map at scale and translate point clouds into fire behavior modeling is through collaborations with some really great innovators in computer science. So it's not just the wildland fuels specialists, but also these important partnerships.
Brett, you're muted.
Sorry. I think we're out of time. Lindsay, I saw Lindsay on, but Lindsay, I'll pass it to you maybe.
Yeah, thanks, Brett. Yeah, what a great discussion, and that was an incredible panel. I know I learned a lot, and I hope that everyone who joined us today also took away a lot of insightful information. Thank you to all the participants who joined us today, and Brett, thank you so much for doing a wonderful job facilitating and moderating today's discussion. And a final thank you to Michael, Emily, Louise, Russ, and Susan. I really appreciated hearing from all of you guys and all of your knowledge. Lastly, as we close out today's meeting, everyone should automatically receive an evaluation. Please take a few minutes to fill out the evaluation. Let us know what you think about this series. And all evaluations are anonymous, and we truly do look at each evaluation. Thank you again, and I really appreciate everyone's time. And we'll see you on the next discussion, which is on February 20th, Social Acceptance and Communication Strategies for Wildland Fire Management.